In this lecture, we are going to discuss another kind of moving average, the exponentially weighted moving average. Note that some other names for this are exponential smoothing and the low-pass filter. So if you've taken some of my other courses before and you've heard me use those terms, recognize that this is the same thing. In fact, this kind of moving average is very applicable in many areas of machine learning, statistics, finance, and signal processing, so you will generally see it pretty often. So what is the exponentially weighted moving average? I want to break this lecture up into two parts. The first part is the short summary. If you want to only watch this part and then skip to the code, that's fine. The second part of this lecture will be an optional, in-depth discussion about why the exponentially weighted moving average has its name. You can opt to watch this if you want to get a better understanding of why and how this works. Okay, so what's the short summary? As you know, the arithmetic mean can be calculated by taking all of your samples, summing them together, and then dividing by the number of samples. The exponentially weighted moving average is calculated differently. In fact, it's calculated kind of on the fly or in an online manner. It says that the moving average at time t is equal to some constant alpha times the sample at time t plus 1 minus alpha times the previous moving average at time t minus 1. In other words, at each step, the new moving average is the weighted sum of the new sample and the old moving average. Alright, so that's pretty much it. It's not a terribly complicated calculation. Of course, without further analysis, it's not clear why this is an average, and it's not clear why it's exponentially weighted. The next part of our short summary is this. How do we do it in code? Similar to the simple moving average, we call a function on our series, or our data frame, called EWM. This returns an EWM object, which is similar to the rolling object we saw previously. It has a similar set of functions, such as mean, variance, covariance, and so forth. To discuss a practical issue, what value of alpha should we choose? Alpha is something like a decay factor. Typically, alpha is chosen to be a small value between a 0 and 1, like 0.1 or 0.2. It might help to look at some extreme cases. So let's say we choose alpha equals 1. That means set the average to be just the latest value of x. In this case, all we're doing is copying x, and therefore it's not really an average at all. On the other hand, let's say we set alpha equal to 0. Then all we're doing is copying the previous average, and we're not taking into account any new samples. Intuitively then, if we set alpha very close to 1, that says new samples matter much more, and the old average matters much less. You can imagine this will lead to a much more noisy time series, which will more closely match the original. If we set alpha very close to 0, that says new samples matter much less, and the old average carries much more weight. In this situation, you'll get a much smoother time series, and it will take a much more drastic change in x to affect the moving average. Okay, so now that the short summary is complete, if you want to know the details behind the exponentially weighted moving average, keep listening. Let's suppose we want to calculate the usual arithmetic sample mean. Using the formula for the sample mean, you might suggest that this is quite obvious. Just take all the values of x that you've collected, add them all together, and divide by the total number of x's that you have. The question is, what's wrong with this? I'll give you a minute to think about it, so please pause the video until you think you have the answer. Alright, so hopefully you thought about why calculating the sample mean naively might not be such a good idea. What if we have a lot, or even an infinite amount of data? Obviously, our computers or our servers don't have an infinite amount of space. And even if they did, calculating a summation is O of t, so the more data you have, the longer it will take, and that will increase linearly with how much data you've collected. Here's my claim. I claim that you can make the calculation of the sample mean O of 1 on each step in both space and time complexity, no matter how much data you collect. Again, as an exercise, before moving on to the next slide, I want you to think about how this might be the case. Please pause the video if you want to take a moment and think. Okay, so hopefully you thought about how you might calculate a sample mean using constant space and time. The key is that you can calculate a sample mean using the previous sample mean. Let's call the sample mean after collecting t samples, x bar subscript t. This means that the sample mean after collecting t minus 1 samples is x bar subscript t minus 1. We can write down the definition of both of these, which I hope is pretty obvious. Now that you know the main trick, let's again make this an exercise. Can you express x bar t in terms of x bar t minus 1? Please pause the video until you've tried this on your own. Okay, so here's what you can do. First, you take x bar t and split up the summation so that you only sum up to t minus 1. Then you leave x subscript t by itself. This is just the last sample you've collected. The next step is to realize that the sum of the x taus from 1 up to t minus 1 can be expressed in terms of x bar subscript t minus 1. We just have to rearrange the equation from earlier. It's clear that this sum is just t minus 1 times x bar t minus 1. We can substitute this into our expression for x bar t to get the sample mean at time t in terms of the sample mean at time t minus 1. One interesting thing you can do, although it's not totally clear why you'd want to do this at this time, is split up the formula as follows. The first step is to multiply out the 1 over t term. That gives us t minus 1 over t as the first coefficient and 1 over t as the second coefficient. The second step is to simplify t minus 1 over t to 1 minus 1 over t. At this point, we can just leave this as is. This is the form that we want. We have one term with the previous sample mean, and we have one term with the latest sample. What's important to recognize about this equation is that we have discovered a way to calculate the sample mean that does not depend on carrying around all of the samples you've ever collected. All you need to have is the previous sample mean, the latest sample, and the number of samples you've seen in total. The next question to consider is, what if we believe that recent data matters more than past data? If we look at our equation carefully, we see an interesting characteristic. Remember that as we collect more and more samples, the value of t is increasing. That means as we collect more and more samples, the weight that we give to the latest sample decreases. We can see that the weight that we give to the tth sample is exactly 1 over t. Now, although this might make you think that the influence of each sample somehow decays over time, remember that this is not true because this is still just a regular arithmetic mean. But what if we want recent data to matter more? What would happen if, instead of making the weight 1 over t, we simply make it a constant, alpha? Well then, this is exactly the exponentially weighted moving average. The basic idea is, instead of giving less and less weight to each new sample, we now give a constant weight to each new sample. Let's see how this affects the influence of each sample overall. The next question we want to answer is, how does this update actually implement an exponentially weighted moving average? Can we show that this is true? And in fact, it's not too difficult. At this point, what we can do is just keep recursively plugging in older and older values of the sample mean. So we can replace x bar at t minus 1 with its representation in terms of x bar at t minus 2. Then we can multiply out the 1 minus alpha term so that we get x bar at t minus 2 by itself. Now we have three terms, x bar at t minus 2, the sample at t minus 1, and the sample at time t. The next step is, of course, to replace x bar t minus 2 with its representation in terms of x bar t minus 3. From there, we can do the same thing, multiply out the 1 minus alpha, and get each of the terms by themselves. At this point, you should see a pattern. The number of individual samples keeps growing, and the power on the 1 minus alpha term also keeps growing. If we keep repeating this pattern t times, we end up with this expression involving a summation over all the past samples from 1 up to t. And of course, these weights are exactly exponentially decaying. Since alpha is a number between a 0 and 1, 1 minus alpha is also a number between 0 and 1. And when you raise a number between 0 and 1 to a power, it gets smaller and smaller exponentially as k gets larger and larger. So how can we summarize what we've learned? In this lecture, we've extended the concept of the mean to include the exponentially weighted mean. We can picture this by assigning weights to each of our samples. With the arithmetic average, each of the weights is just constant, with equal weight for each sample. With the exponentially weighted average, the weights decay exponentially going backwards in time. This means that the latest sample matters the most, the second latest sample matters less, the third latest sample matters even less, and so forth.